Hello everyone. Today's bit of code to walk through is an example of how to process a data file that is too large to fit in memory using Python. The specific problem that we're faced with in this particular notebook is being able to find which molecules out of a set I have are present in a very large file. Specifically, I've got a set of molecules that I've run some calculations on, and I want to see if they are from any of these different subsets of molecules collected by the ENCOVE team. For example, I'm trying to find which molecules that I've searched are in zinc 15, which is a 80 gigabyte file of SMILE strings. And while my particular computer I'm working on, a server run at ALCF, has 512 gigs of memory, it's bad form for me to read and use about a quarter of that memory myself. So, because it's a shared resource. So what we're going to use is Python's generator objects instead. So the core bit of this notebook here, I'll paste a link to it in the description of this video, uses generators. So what generators are they're functions that produce new data on demand. And you know that a function is a generator function by this word here, yield. So what this function does is it runs up until the point that it hits this yield function and it produces data. At that point, it waits for it to be called again and then reads through more data and to produce another chunk. So in this way, I iteratively read through the file rather than all at once. In fact, you use generators a lot in Python if you ever read from files. This file pointer here doesn't read the entire file in at once. It does so only when you ask it to. So that allows me to build this sort of iterative algorithm. And so that produces my data in chunks. I then create a function that will process one of those particular chunks. Here, I'm taking a list of molecules that I read from that file and doing some processing to see which ones are contained within that set of molecules I've done the computation on. So the short of it is once I have that generator, which produces data, I can then run the matching function on that chunk in order to find which ones match. So I'll run this bit of data here. I'm going to run it on this code here. I'm going to run it one of our smaller data files, QM9, which only has 100,000 molecules rather than PubChem has 100 million. So let's go ahead and run this. I'm going to restart and clear everything so you can see it from scratch. And I'll walk you through the important bits. So this actually may take a second to load in on memory for the notebook, which actually means I may end up editing this because you're going to watch this Jupyter notebook file to take a long time. So now I'm back. I should have edited that part out. And what you're going to see here is I've read up to this point in the code, and by the time I got down to this file, it had already ran. So let's show you a little bit about what the cores are for this. So if I call read in chunks for a file path, file is the path for one of these data files, you see it produces a generator object. Now, a generator object produces sets of data on demand. So you see here I've read in some files, if I call it again, it produces a different chunk of molecules because what's happening is each time I call next, it goes through and continues until it hits another yield statement. So that's a generator. Now I can take these chunks and I can pass them through my function. So I can do and pass that through a loop. Now, the bit I wanted to show you after I explained that generator was that I run these functions in parallel. So first thing I do is I create a partial function that contains matched molecules and fixes one of the two arguments that is going to stay the same every time I call it, which keys I'm matching against. I use the partial functions rather than a lambda object because it plays nicer with multiprocessing. Partial functions can be serialized, pickled, and passed to the subprocess. Lambda functions cannot. And here you see I take my function, I pass it to the IMAP unordered operation, which means that it only calls the generator function to create new data to run as soon as one of the workers has finished. And the unordered part is means that it will return data for me to process as soon as any of them complete. It doesn't matter which one created first. So now that I've got explained what that works, I'm going to show you what happens here as well. Let's run one of our bigger data sets. So QM9, it's going to take about 3 seconds, but PubChem is going to take a longer time. So if we go back and open up our sub-process or our process viewer, you can see that I've got 32 threads running. Each of them is using roughly one processor core. And if we go back to here, we can see that it completes roughly in wafts of 32. So yeah, here now I've got a parallel version of this code. To remind you, the way that I minimize memory usage is I create a generator function such that it only reads out data when I can compute on it, and I parallelize it by using the IMAP function, which is a parallel version of the multiprocessing pool that works with generators. And for another optimization, I use the unordered version because I don't care about getting results in order. So that's all for today. Thanks everybody for tuning in.